the method of corners. We're going to consider an optimization method here for linear programming problems called the method of corners. Hopefully you've already taken a look at it and have a bit of a familiarity with what it is and how it works. The calculator, with its ability to graph not only lines but linear inequalities, is a useful tool for helping us to solve method of corner problems, or these type of linear programming problems. The limitation of the method of corners is that since it is graphical, it can involve no more than two variables, since we can only graph on a flat surface like our calculator screen or paper in two variables, one in a horizontal axis, one on a vertical axis. So let's take a look at this problem here. It does involve two variables, and in this case we're asked to maximize p is equal to 3x plus 2y. That's our objective function. We want to find values of x and y that give us the largest value possible for p, subject to this list of constraints. 2x plus 3y is less than or equal to 12, 2x plus y is less than or equal to 8, and both x and y are non-negative. Now I see here at the bottom I've already written up the solution here. We'll note that the x and y non-negative tell us that we're looking at the first quadrant only and along the axes that border the first quadrant. And if we take the first two constraints, 2x plus 3y less than or equal to 12 and 2x plus y less than or equal to 8, and solve both of them for y, we get y is less than or equal to negative 2/3 x plus 4, and y is less than or equal to negative 2x plus 8. We need to do this in order to be able to plug these inequalities into the calculator. Our calculator really graphs functional type things, and that means that we need to get that y by itself on the left-hand side. Now, as we did in the previous video that talked about graphing linear inequalities, I'm not going to actually tell the calculator to shade the less than or equal to's. I'm going to tell it to shade the opposite. And that's going to give me a nice clear area so I can very clearly see where my feasible region is. That is the area in which my solution can come from. So let's go over to the calculator and let's type in those two inequalities but in equation form. So we're going to have negative, and then again, just because I like to be careful, I'm going to put the 2/3 in parentheses. So negative, and in parentheses 2 divided by 3, or 2/3. That's times x, and then that is plus 4. That is our first one. And then for the second one, we're going to have negative 2x plus 8. And I'll press enter to store that. Now in both cases, the inequality is less than or equal to, so I want to shade the opposite, or greater than, which means I want to shade above. Alright, the second inequality here, if we go over to the left, is already set for shading above. So we're already ready there. But we need to change the shading on the first one. So we'll press the enter key as many times as we need to scroll through our various options until we eventually get shading above. And there we go. Now we're going to shade both of those above. Now, something else I know, well, actually, let's try this first. I'm going to press zoom, and I'm going to do a standard zoom. This isn't correct because we're not interested in the second, third, or fourth quadrants. But I'm going to do this first just to get a rough picture of what goes on. And then I can go back in and adjust the window to force myself into the first quadrant only. So here the calculator is graphing the first of those two inequalities. This is negative 2/3 x plus 4, or if you want to think of it as it's written in the problem, this is graphing 2x plus 3y less than or equal to 12. But again, doing the shading the opposite, so the unshaded area is the solution region for that inequality. And the same thing is now happening for the second inequality. And again, we're shading the opposite, so we're interested in the unshaded region. So if we look here, it's kind of small on the calculator, but we get this little four-cornered kind of wedge here in the first quadrant that is underneath all of the shading. To see that better, I'm going to change the window and set the x min to 0. I'll leave the x max at 10. And I'm also going to change the y min to 0. And that's dealing with the third and fourth constraints, excuse me, x greater than or equal to 0 and y greater than or equal to 0. So once we've done that, we can press the graph key again, and we can get a better picture here of what's going on. So the calculator, again, on my computer, unfortunately, slowly will graph the first linear inequality, and then once it's done with that first linear inequality, it'll graph the second one. And I will remind you again that I'm shading opposite of the way you probably would on paper, because I think it's easier on the calculator to see the white area as the feasible region, or the region from which our solution will come. Now what I want to do here, as this is finishing graphing, is I want to note the corners of this region. We have a corner here at the origin, 0 and 0. I have a corner here at the lower of the two y-intercepts. I have a corner here at the intersection of the two lines. And I have a corner here at the x-intercept of one of the lines. In this case, kind of the smaller x-intercept, or the one that's further to the left, if you will. All right. So we need to go through and figure out what those corners look like. Well, using the calculator, we can get two of them, and the other two we can get just directly from what we see here in front of us. Now the origin we know is 0, 0, so that's the first corner that I have here at the bottom of the example. And if we plug 0 in for x and 0 in for y into our objective function, which is 3x plus 2y, we get 0. All right, that's probably not going to be our answer, but we should always check all corners. It's possible that could be an answer in a minimization problem. If I work my way clockwise around this region, the next corner is going to be the y-intercept, and it's the smaller of the two y-intercepts. If we inspect the two inequalities that we have here, we see that the first one has a y-intercept at 0, 4, and the second one has a y-intercept at 0, 8. So the smaller of those two is 0, 4, or the lower one. And that's what I've written down for my second corner. So 0 and 4. Going to our objective function, plugging 0 in for x and 4 in for y, we find that our objective function takes on the value of 8 at that corner. All right, moving around here to the intersection, you can use the capabilities of the calculator. I'm not going to go through that. That's been done in other videos here. But you can use the capabilities of the calculator to find that intersection of those two lines there. And when you do so, you'll find that the two lines intersect at 3 and 2. And if we take x equal to 3 and y equal to 2 and plug that into our objective function, we'll find that p is equal to 13 at that corner. And finally, coming down to this x-intercept. X-intercepts we can find using the 0 functionality in the calculator. If you go to Second and Calc and then choose the 0 option, you can use that to find this. You'll need to adjust your window a little bit because you'll need to see a little bit below the x-axis to do that. But that's how you would get that. And again, that's been discussed in other videos. But when you do that, you'll find that you'll get 4 and 0 for that x-intercept. And if we plug 4 in for x and 0 in for y in the objective function, we'll get p is equal to 12. So we can use the calculator to help us find the shaded region, and for some of the more difficult corners like intersections and x-intercepts, we can use the calculator functionality to find those as well. In this case, we find out that our optimal solution is when x is 3 and y is 2, and that gives us a maximum objective value of 13.